I'm very unlucky. I have the worst session of the day because I'm going to sit here and talk to you about software and visualizing things and looking at it from another layer, how to get better understanding. And what you guys are going to be thinking about is beer. How many of you are going to the after party? Everyone's thinking about the after party. No one's that interested in the talk. But I'll do my best to try to keep you entertained for at least an hour. How many of you have walked into a new piece of code before that you've never seen? You show up, first day of work at a new project, crap. How many of you have spent at least 2 or 3 months trying to ramp up on a code base? I am in an unfortunate position. Very often, I come into a client and I will be there for a grand total of 3 days. How do I tell them something valuable about their software in 3 days? What we're going to look at is we're going to look at things that I do in order to help me gain understanding of that project within the first 3 days. We're going to go even more in depth. How can I walk into a source base in 2 hours and tell you where your problem areas are? There's ways of doing this, and they're very valuable to understand. How many of you use source control? We tell our business people over and over again about how valuable their data is and all the things they can learn from inside of their data. It's real business value inside of data. How many of you data mine your source control? Why not? We tell the business people about this data that they're recovering and how valuable it is, yet we have all this data that we don't use ourselves. The first thing that we can go look for in order to really get to know a source code base is go look at the source control. How many of you have seen this screen before? It's telling me a whole list of commits. Why do you commit? You changed something. Why'd you change something? It was a new feature? It was a bug? Well, there's a couple reasons why we do it. Now, if I were to think about what you should see in source control, and I'm not very artistic. I'm slightly autistic, but not very artistic. This is what we should see on a healthy piece of code. If I were to graph the number of check-ins or commits over a period of time on this file, this is healthy. At the beginning, we get a big spike. Then we're done, and we see it flattens out, and we don't get any more commits, and then maybe we see a commit here or there. This is healthy. Think about it. You write code, you get it to the point that it works, and then you don't touch it. You should not be continuously changing code. What I tend to find in source control is not something that looks like this. I tend to find something that looks like that. What this is telling me is that you have a bug hive. It's either you have tons of bugs in this code, and you're constantly going back and fixing it, or this code is very, very coupled. But you're changing other unrelated things, but they cause you to have to make a change inside of this code. How hard would it be to take, I don't know, link, which has an adapter to Git, and to produce this chart for me? I've written it, I can tell you. It's about 19 lines of code. It's not hard to go through and get this kind of chart out. But this, I can run across your source base very quickly, and I can look to see if I'm seeing this or if I'm seeing that. Places that I find like that, those are very interesting places. I'm going to go in and I'm going to look at that code. Places where it looks like the first one, I'm not going to bother looking at that code. It's not your problem. Your problem is when you get this. There's lots of these kinds of tools that we can use to get in and look at our source control. And this Mac is terrible. It keeps going out of full screen. How many of you have heard of Gorse? So what we're looking at here is a visualization of the commit history of jQuery. And hopefully the Wi-Fi won't go down. We notice patterns when we look at this. When you watch this, you are watching the history over the course of months, sometimes years, of how this software came to be. You see patterns when you start watching it. You should see a whole bunch of things come into it, and that's lovely. There. What we see is the committers coming in and working in different areas. This is a very simple visualization that we can use to get a better idea about the history of this software. And you generally don't want to see 10 people all hitting on the same thing. You should see it come out and then come back. You'll see it expand and contract. Think about how you write code. You go through and you write something, and then you realize that there was something that you could have done and abstracted. You had the same thing written 10 times, and you come back and make something that generalizes it. You should see expanding and contracting. These are all ways of identifying and visualizing things about our source code. The big problem when I come into a source code base is that I don't know it. I don't know all about the history of the code. I don't know where the problems are, and there's 1.5 million lines of code. What we need is better ways of finding the interesting places. What you're really interested in, if I come to your company, is that on the first day, I can tell you where your pain is. I can say, this is where it hurts right now. These are tools that allow me to do that. And we're going to go through more of these kinds of tools. But the easiest way, and the first thing that I look at, is the source control. I data mine source control. And if I see this, that is a place where you have pain. And it's a place where you feel pain. Do you know how I know that? Because you commit. You're committing. You're telling me that you're actually changing this stuff and that it hurts. But this is not the only way of visualizing code from higher levels. How many of you have heard of tools like Sonar or Append? They're wonderful tools, but there's some problems with them. They give you too much information. If you want to watch an architect's head explode, give him a copy of Append. It will tell him everything that he never cared about his system. Finding the real information inside of these tools and finding the important stuff is the hard part. How many of you have heard of Afferent and Efferent Coupling? Those are really big, fancy words. We're going to go in and we're going to define what they are. But it's always been amazing for me that we as developers in university don't learn about Afferent and Efferent coupling. How many of you have heard that you want to create software that is low coupling and high cohesion? Have any of you stopped to wonder what kind of cohesion? Because there's like 8 different kinds. No one ever talks about that. They just want it to be highly cohesive. And we're going to talk about some of the different kinds of cohesion as well. This is one of the screens from Append. That's a lot of information that it gives you. The trick is trying to get in at the right information, and that's hard. So what we're going to do is we're going to start learning about some of these kinds of code metrics, what they mean, and how to interpret the results. Now, there is no code metric that I can give you that will say, this absolutely means that this software is good. This absolutely means this software is bad. What I can give you is I can tell you this is an interesting place to go look. There's probably something going on here. And when you start realizing what these metrics mean, you can look at code from a very, very high level and drill down into the places that are interesting. So let's start with afferent and efferent coupling. They're very big, fancy words that basically are extraordinarily simple concepts. Afferent coupling is the number of people that couple to me. Efferent coupling is the number of people I couple to. It'd be a whole lot easier if they called it coupling in, coupling out, wouldn't it? Instead of having words like afferent and efferent that make it sound like some PhD paper. It's a really, really simple idea. Here, We have a method A, which calls B and C. A has an efferent coupling of 2. B has an afferent coupling of 1. It's a really easy idea. And it doesn't just apply to methods. It can apply to classes and dependencies. What we're talking about is what you depend on versus what depends on you. We can do it at package levels. We can do it at a namespace level. What things depend on this namespace? What namespaces does this namespace depend on? It's a really, really easy idea. If we were to flip it around, now we have B and C that call A. So A has an afferent coupling of 2. B and C have an efferent coupling of 1 that couples to A. This is a very simple idea. Stay away from the big fancy words. Just remember it's coupling in, coupling out. If you understand that, you can get a huge amount of information out of your system. What if you had a method that had an afferent coupling of 475? You probably don't want to change that code. What if I had a method with an efferent coupling of 900? Probably says refactor me. Not positive, but it probably says to refactor me. Tools like Append or Sonar can tell you what the afferent and efferent couplings of things actually are. What's really cool with Append is it actually has like a SQL-like language as well, where you can write queries. Select from my code any methods that have an afferent coupling greater than 20. It's a really cool way of being able to look at your code. Now, it's not quite so simple when we talk about couplings, because there's different kinds of couplings. Does it make a difference to you whether I couple to an interface or a concrete class? If I'm coupled to an interface, can you change the implementation? Sure. If I'm coupled to a concrete class, yeah, that'll be fun. So we need to look at what we call the abstractness of our coupling. And the abstractness of coupling, it's, again, a very complicated term with a really simple idea behind it. It's the number of abstract things that I couple to over the number of concrete things I couple to. Really simple metric. What percentage of things do I end up going to that are abstract versus what percentage are concrete? And here we can see that A couples to IB and IC. By the way, how many of you put interfaces as I whatever, I can has cheeseburger? This has always boggled my mind in the .NET community, that for some reason, Hungarian notation is bad, but I can has cheeseburger is good. Well, of course, I can have cheeseburger is good, because they're very cute cats. When we talk about coupling, we need to remember the abstractness of the coupling. Are you coupled to an interface, or are you coupled to something concrete? Again, these are just simple counts, and we can get them out of these kinds of tools. If I understand what they mean, it tells me a whole lot of information about your software. What I'm looking for is places that have high coupling. If I find you have high coupling, and I find that you're changing the code in your source control a lot, that's an interesting place to go look, isn't it? Let's look at the code and figure out why this is like that. Is there some history about this? This is one of the main tools I use to get right into the interesting places inside of your source code. The main problem we have getting into somebody else's code is finding the interesting stuff. It's finding where pain is. These kinds of tools are what will allow you to be productive on that first day, because you can immediately drill right in on the most painful part of the software. There's other ways of viewing source code from a higher level. We're going to talk more about it, but this is an example of it. What we're seeing here is the couplings inside of source code as a graph. This is telling me about the affected graph add connections method. We can see that affected graph merge calls it, and then there's 3 tests that call into merge. This is, again, another way of looking at our code. That's what we're focused on. How do I get higher level viewpoints of code to help me find interesting areas and to drill down into them? You could be looking at code coverage. You could be looking at afferent couplings. Just remember, if you look at them, to consider abstractness. There's all of these different kinds of ways of looking at code. How many of you have seen this before? This is a report from Endepend. So we're going to go through really quick, and we're going to look at some of the kinds of things that it can show us. How many of you have heard of a dependency matrix before? So what this is talking about is who has dependencies on what. What you don't want to see is what's known as circular dependencies, things that are dependent on each other. That's bad. If you bring up this graph and you have circular dependencies, what you will actually get is black. And they will show up in the middle, and they'll be black. What you ideally want to see is kind of what we're seeing here. You see the blue at the bottom, and then the green going all the way up the other side. That's showing that we don't have a huge amount of interrelated dependencies. This is actually a good thing. This is doing it at a package level. We're looking at a package level, how the packages depend on each other. As I said with afferent and efferent couplings, we can do this on any level. Namespaces, classes, methods. It's the same thing that can just be applied at different levels of granularity. Let's jump back. And let's go in really quick and look at some of our application metrics. So we can see, and this is for DB, for objects. It's got 31,000 lines of code. We can see the number of IL instructions. Our code coverage, they actually have very bad code coverage. It's only 39%. This is giving us a high-level viewpoint. But we can start getting into a lot more detail. And this is one of the most valuable things that Endepend will actually give you. I mentioned before that you can come in and you can write SQL-like queries. Well, what they've done is they've written a whole bunch of these SQL-like queries for you. So, for instance, it may be looking for methods that are too complex. That's the second one there. What that's actually using, we're going to talk about it in a few minutes, is cyclomatic complexity. But it may be, what about methods that are too highly coupled? I'm very interested in any methods that, as an example, may have an efferent coupling greater than 20. So show me a list of them. These are just pre-done ones. You can write your own as well. What if you had a class that had 245 fields in it? Chances are that's not quite right. What about a method that had 25 variables? All of these are smells. They're things that if I see this, it doesn't necessarily mean it's bad. I'll give you a perfect example. Cyclomatic complexity. I wrote a method that had a cyclomatic complexity greater than 2,000. It was a state machine with gotos. It was very, very complex if you took the metric, but it was a state machine. There's actually a couple methods inside of the .NET framework that are like this too. Remember that when we talk about these things, you don't want to say, I'm going to optimize to get none of these errors. Because a lot of times they can be false positives. You have to take the number and use it as a tool to help you go and find areas. Do not take it as if you have a cyclomatic complexity greater than 20, you are a crap coder. That's not true. Sometimes you want to break. It's not always bad. And it's very important to keep this in mind because one of the biggest failures I find with teams that start using this stuff is they try to optimize to say that we're not going to get any lists. Nothing will be in our list. Because obviously the people that built the metric tool, they know much more about our software than we do. Keep in mind that these are pieces of guidance and they are not necessarily always accurate. You use them to identify places. You do not use them as a rule. You do not set up rules, let's say gated check-ins. That's my favorite one. You cannot check in code with a cyclomatic complexity greater than 25. I actually know teams that have done this. Don't go down that road. use things as a tool, as a heuristic towards finding interesting places of code, because you guys are all developers. You can go read the code. Go talk with that developer. Go ask them why they did this. Why were they putting in that code? Going along with this, how many of you use continuous integration? For me, what's really interesting about code metrics is not necessarily a static view like what we're seeing here. What I'm interested in is deltas. Deltas give you a whole big piece of information. I want to know about how things are changing. Are you going through and adding more coupling to the code or removing coupling from the code? If I look at the code that you're changing, are you adding complexity or removing complexity? These are the kinds of things I really like to look at. And it's very easy to set up a tool like this to run inside of your continuous integration server. And when you do that, it'll generate deltas from one run to the next. Because they're also tied to check-ins, that means you can actually look at which check-ins caused which deltas. If I were to go a little bit more with the idea that our data is valuable, what could I start telling you about your team members? By looking at all of their check-ins in big groups and looking at the deltas and the metrics over large numbers of check-ins. There's a huge amount of information here. The real trick is not so much getting the information, it's understanding what's important and what is not important inside the information. It gives us too much information. But let's take a quick example here. Let's try methods with too many overloads. That's always a fun one, right? It will tell us what the query is. And one of my favorite things about all these rules they've built into Append is they show you the actual SQL-like language that they're writing in order to represent the rule. So here we can see that we'll get a warning if count is greater than 0, where the number of overloads is greater than 6, and it's not an operator. Think about that for a minute. That's a huge piece of information. How many of you have written a method that had more than 6 overloads? Come on, you can admit it. I've done it. If I were to come into your code and I were to run something like this really quick, is that likely going to be an interesting spot that I could go fix? If I went and fixed that, would that likely improve or not improve the quality of your code base? Would that be a good commit that you would like to see from me on my first day? What about when we've got a method that's very complex, and I jump in really quick and I refactor it down, and I put in less complex code? These are the kinds of things that can be done because we've identified valuable areas of code to jump into. We're finding where people are having pain. Now, there's all sorts of other things that we can start looking at. For instance, we can start looking at how assemblies are dependent upon each other. We can look at how namespaces are dependent upon each other. Classes, methods. How are things intertwined? We looked, for instance, at the dependency matrix that showed us a matrix of our dependencies. I can tell you, a lot of systems you go into, you'll bring it up and they'll just come up black. Everything is dependent on everything. And you know what the problem is immediately. A couple of years ago, they actually have a really funny report. It's one of these for the .NET framework itself. When you brought it up, black. They had methods with cyclomatic complexities, which we'll talk about in a minute, greater than 500. Again, all we're doing here is we're identifying interesting areas. None of these metrics will say this is good or bad code. What they do is they give us ways of looking at the code that are different. It's a higher level view. I can look in this one report at 1 million lines of code. And I can start getting some understanding about how this code is intertwined. I can start seeing where problem areas are. Again, this is just more data, and our data is valuable. How many of you have told your business before that your data is valuable? These are all just different ways of looking at what we're doing. So let's just jump back. Now, I have to go into another tool. How many of you have heard of Mighty Moose? So Mighty Moose is a continuous testing tool. When you save or when you type, it can figure out which unit tests need to be run, and it does that in the background. It's actually a fairly interesting tool. It was very fun to write, I have to say. But that's not its main value. Its main value is because I can run your tests, and because I'm running them, I can start getting information about them. I'm running your build, so I know when your code changes. I have all the information about all your code. I can start giving you higher level viewpoints of your code. And we mentioned this one to start with. This one is a graph that's showing how pieces of code are related to tests. How many of you have sat in a piece of code before and wondered how many tests and which tests were covering this code? It's a fairly common thing to wonder. I'm going into the code for the first time. Does it have any tests? All of this is information that I need. If I walk into your code for the first time, I've never been in any of your code, I open up the file, I could start making changes, right? Except I'm afraid. I'm scared to change this code because I don't understand all the code around this code. Again, this kind of data can start helping us become comfortable with changing code. If I'm not comfortable, then doing a very small change is going to take me a long time because I'm going to go look all around this code to the point where I feel I understand it and I'm not breaking something. That's where my time gets lost. My time is not so much just doing the change. It's understanding everything around my change and making sure I'm not breaking anything. What tools like Mighty Moose can give you is this confidence. And we're going to go through various ways that you can start getting this confidence. Now, we talked before about Efferent and Afferent coupling. Mighty Moose uses Afferent and Efferent coupling. You can see here how we actually have some couplings inside of this code. What that's doing is it's using those couplings to build up this graph. This graph is showing you Afferent and Efferent couplings. Nothing more. It goes in at an IL level and looks what things you call. It then puts together a graph that shows you how things are related to each other. Now, it's very interesting. After having used it for quite some time, I started finding patterns in the graphs. And some teams I've worked with have even named patterns inside of graphs. As an example, they have a teapot. If you see a graph, I don't even need to read the nodes. If I see a graph and it looks like a teapot, I know the refactor I have to go do. You cut off the nozzle. Healthy code, when I see it like this, will look like a spaceship with a big engine. Unhealthy code looks very different. And if people go and use it, sometimes you'll get into really coupled code. And my favorite feature suggestion that we ever had was, well, when I bring up the graph in this code, the graph has like 800 nodes in it. And, well, I can't read the nodes because they come up too little in the graph. And so it makes me zoom in. That's not a problem with the graphing system. Just bringing up a graph without even reading what the nodes actually say on them, I can tell you a lot about your code. Would you consider that to be reasonably healthy code, looking at the graph? What if we were to try a different graph? We'll shoot ahead. What if you saw that graph? It's actually not that bad. I've seen much, much worse than this one. This one does kind of look like a spaceship, but you'll notice that it does not have big engines. Again, these are just ways of visualizing and understanding our code. Anything that you can do to get a new way of looking at a problem will help you with that problem. So let's just shoot back. Now here, we've got some couplings going out in our code. We've got one to nodes.containsKey, and another one to the constructor of node connection, and another one to connections.add. But there's also something else interesting going on in this code. You guys have heard that you want low coupling and high cohesion, right? That's what code is all about. But I find it odd when I talk to developers, nobody actually knows what cohesion means. Well, of course, it's cohesive. It makes sense. Well, okay. But there's lots of different ways of dealing with cohesion. There's data cohesion. There's functional cohesion. There's procedural cohesion. Which cohesion do you want to use? One metric I love looking at, you can see here. Here I've got two fields. I've got nodes and connections. And I have this method here. This method accesses nodes and it accesses connections. So we could say that from a data perspective, this method is 100% cohesive. It accesses all the state. I could put another method in here that accessed neither nodes or connections. And we would say that that was 100% non-data cohesive, because it accesses none of the state. How many of you have written or set a goal that when you write an object, every method should touch every single piece of state? That doesn't sound like fun, does it? Because normally what happens is you end up with 5 methods, and maybe we've got 10 fields inside of here, and each of the methods is accessing, let's say, 5 or 6 of the different fields inside of our object. You generally don't want to become 100% cohesive, and you don't want to be 100% uncohesive. You're somewhere in the middle. It's a good metric to look at. How many of you have heard of single responsibility principle? I've always had fun with single responsibility principle because I've actually had someone tell me that if I follow single responsibility principle, what I should build is an anemic domain model with no behavior in it, and then put services all across the top. Because that's single responsibility, one service for every behavior. But they're leaving out one of the core concepts of object orientation. What is the responsibility of an object? If we say that we're single responsibility, that falls into what is the responsibility of our object. The responsibility of an object is to encapsulate state and provide behavior. If we follow that, all of a sudden this concept of data cohesion becomes very important. How do I figure out whether or not a method should go into this object? Well, I can start looking at the state and how it's accessing the state inside of that object. How many of you have put a method onto an object that accessed none of the state in the object? Could that be a code smell that that method should not go there? We can use a lot of these kinds of metrics when we're coding as well. And most of them are extraordinarily simple. I can explain most of them in less than 5 minutes to a junior. They have fancy names associated with them. Academia has gotten all into them. But they're not difficult concepts. It's more, they have difficult names and they're not approachable. When you actually understand them, you can get right into this. Now, how many of you would see this code and think that we should refactor it? How many tests does this code need? I'll give you a hint, it's more than 6. If I have an and there, that's probably going to need 2 tests, right? How could I figure out how many tests this thing's actually going to need if I want to cover it? I could count the conditions. How many of you have heard the big fancy name cyclomatic complexity? Okay, let's try it a different way. We count the branches. Fancy, fancy term, simple idea. What we do is we count the number of branches that exist within a given piece of code. That's it. If you got an if statement, well, that adds to your cyclomatic complexity. What would happen if I saw a method, and I'm not going to say cyclomatic complexity, that had 47 branches, 47 possible paths through this method? How many of you think there's going to be 47 tests there? If I knew that there were methods with 47 branches through them, 47 paths, would that be an interesting place to go refactor? If I use a tool like Sonar or Append, yeah, it'll actually tell me that. It'll tell me what the cyclomatic complexity of all my methods are. Again, this is another way of drilling into the really interesting pieces of code. Do not take this and say, we have a gated check-in. If anyone ever puts in cyclomatic complexity greater than 25, we will reject their check-in, because we are the source code Nazis. You don't want to do that. You use it to find interesting places and to gain understanding from a high level. Now, another thing that we threw into Mighty Moose, and this is actually, it's very odd because it's the most valuable thing for me. And it came as a byproduct. There was actually 2 bits that were byproducts. The first one was the graphs that I put up, these. Do you know why those were put in? That was my debugging tool for working with the coupling and trying to figure out which tests to run. It was just a little visualization that I could use to see what I actually thought was coupled to this code. And after a while, I started realizing I was using them all the time, not just to look at the coupling graphs internally. I was bringing them up to understand code. There's another one of these things that came in. We talked earlier about if I come into your code, I've never been there before, I'm scared. Not because your code is so god-awful. I'm scared because I don't understand the context of the code. I don't understand what's going on around it. What these little buttons here will tell me is they'll have a number. That number is how many tests cover this code. And then we do a risk analysis of your code. That little button turns from green to yellow to red. And there's actually a hidden feature inside of there as well, which it'll turn into a dragon. I won't tell you what you have to do to get your code to make a dragon. But if you fix a dragon, it will also reward you. If I see green, I'm comfortable. Now, green does not mean that your code is awesome. It means I've got a tool that's doing a risk analysis around this code for me. It's not green is good code, red is bad code. Green is code that if you make changes, we feel confident that the tests will likely find things if you break them. How many of you have heard of code coverage before? Code coverage is absolutely useless. It is nothing but a false sense of security. How many of you have written a test and forgotten to put an assert? Does that test still cover stuff? But there's no assert, so what is the value of this test? How many of you have put in an assert that was absolutely meaningless compared to what your test was supposed to do? I know, and not you guys, but juniors do it. And then I get back my code coverage report that tells me I've got 99.4% code coverage. Yes, great software. Except none of my tests have asserts inside of them. Code coverage is almost meaningless. What's really interesting is not how many bits are actually covered by a test. What's more interesting is when I look at tests from the perspective of, I've got some code, I've got some tests around the outside. If I were to bring up this graph. The yellow ones are the tests. The green one is the node that I was searching for. Do you think those tests are likely to assert off something related to the thing that's under test? What if there were 19 methods in between? In other words, we had 19 things between us and the test. Do you think it's likely that the test is accidentally covering us? Do you think it's probably likely that it will assert off anything to do with us at that point? Probably not. So what the risk metrics are looking at is they're looking at how far away these tests are from you. They're looking at your cyclomatic complexity. I know another big fancy word. We'll just call the number of possible paths through your code. So I know that there's 19 tests. I don't know the quality of the tests. I can't possibly know that. We'll talk in a few minutes about an interesting way of trying to determine that. They are a call path of 3 away. Do you think this is risky code to change or non-risky? I didn't add one part. The distance, was the distance in a test assembly or was it in code? What was the complexity of the things in between? All of these come into play. If I have a method between you and me that has a complexity of 5,000, you're probably accidentally covering me. In other words, each path along the way is a multiplier. Again, these are just ways of visualizing and understanding and trying to quantify risk associated with code. How many of you have been scared to make a change before? The little green dot does not tell you that your code is awesome. It's just a quantification of our perceived risk around what you're doing. If I go in, not all code will be green. Sometimes it'll turn yellow or red, or as we mentioned earlier, dragons. This one is giving us a yellow 5. That means there's 5 tests that cover this, but yet we still think it's risky. I bet if I actually looked at code coverage, almost all this method would actually have code coverage. But we still think it's risky for you to make a change. What this is this is a signal to you. Look around. Before changing code inside of this, I want you to look around what's going on in this. You're probably going to have a problem. More research needed. It doesn't mean crap code. It's just an indicator to tell you when to go look for more information. Now, we looked at this graph earlier. I mentioned that you'll find patterns inside of these graphs. I've been working really hard to automate this process. But you see that point of inflection there? So I've got all these tests down here that are not covering that code up at the top, and they're all connected through one node. Maybe I should refactor to put an interface at that point of inflection, at which point all that bottom part of the graph would go away. You can find huge amounts of information when you look at code from higher levels. These are the kinds of patterns I'm discussing that you start seeing when you deal with things visually. One thing I've also noticed, when I have a team who is constantly looking at these graphs, they produce less complexity in the graphs than teams that do not have graphs. Why? Because they're constantly looking at it. If I give you something that you constantly look at, you tend not to make it so that there's 900 graphs inside, or 900 nodes inside the graph. Why? Because you start using them. When you bring up a graph, you can arrow through it and hit enter, and it brings you to that place in code. Think about when you're writing code. Where do you normally navigate to? Some arbitrary place inside of your software? Or something related to what you were just working on? almost always the place you want to navigate to is something that's inside the graph. When you start using it all the time and you're bringing the graph up and down, let's say 500 times per day, you tend not to put lots of complexity and make the graph really complicated. If you send me a bug request that the graph doesn't look good for your software, it will be marked not fixed. That is not a problem with the graph. Now, how many of you have seen something like this before? We talked about really complicated, fancy names. This is when we start talking about cyclomatic complexities again. Now, let's talk a little bit about those cyclomatic complexities and tests. How many tests should there be for a piece of code? Enough, yes. Should there be more, less, or equal to the number of possible paths through that code? Less necessarily isn't going to work very well. That's basically guaranteeing there are paths that you are not actually testing, assuming you're only testing one thing per test. I know a lot of people like to test 19 things inside of one test, which makes it very complicated to try to figure out what that test actually means. If I have tests and I know how many possible branches there are through your code, the only other question that I need to answer is what is the probability that this thing is actually somewhat testing this other thing? Is it accidental or is it intended to be testing this? These are very simple ideas, but they can be very powerful. It's different ways of looking inside of our code. What we really want is we want to remove our fear. This method's yellow. It has 6 tests. Do you think it needs more or less than 6 tests? And I won't even get into what that code actually does. I'll give you a hint if anyone wants to read it later. It's actually going through and walking back in IL to fields and delegates. It's not fun code. But I'm getting a yellow here. Would you be afraid to change that code? Would it be beneficial for me to give you a report of all of the yellows in your software, and all of the reds, and all of the dragons? This is how I come in and I can be productive on the first day inside of your source base. I'm using tools that let me look at your software in different ways. I'm removing my fear. When I come into a new piece of software, what stops me from being productive is fear. I'm afraid of what I may break. How many of you have sat for 2 hours looking around before you changed one line of code? Fear is what prevents us from being productive. Changing the one line of code isn't hard. You can do it very quickly. But what does that affect? All of the things we're looking at are ways for me to gain a better understanding of what's connected together, what this may affect, what it may break, what is my risk when I'm working in this area. All of these kinds of tools can be extraordinarily valuable. But if there's one thing I want to stress very hard for you guys, do not take these as your code is always bad if it has a cyclomatic complexity greater than 20. Only an idiot would write that code. What you look at here is you use these as guides to help you find interesting problems in the code. Something that has an efferent coupling or couple out of 23 is an interesting area of code to go look at. It doesn't mean it's wrong. It's interesting. All of these kinds of metrics allow us to find interesting areas and to get into them as developers and research them more. So we've gone through quite a few ways of getting more data about our code. We're data mining our source control. And remember, when we data mine our source control, we want to see it go up and then go down. If it goes up and stays up, you either have a bug hive, or this is heavily coupled code, and other ancillary changes are requiring changes here. We went through and we started looking at Afferent and Efferent Coupling, which are well-known code metrics about how dependencies are interacting. We can use tools like End, Append, or Sonar to get this kind of information out. How many of you are Java developers? There is also Xdepend, which will do this for Java. And I've heard rumors that there's a new version coming out that's going to be for some other platforms. I can't go into details as to which platforms this will be, but if you happen to be doing other kinds of development, it will be coming soon. And we've also looked at how we can even apply some of this in order to calculate things like risk of change to a given area of code. All of these, again, are just data points about our code. It's another way of looking at our code. And the more ways that you can look at things, especially when you get higher level perspectives of your code, the more quickly you can find where problem areas are. The more quickly you can identify areas that may have problems. But again, all of these are heuristics. None of them are completely correct all of the time. A lot of it depends on the style of your code. A lot of it depends on what kind of code you're actually working with at that time. If I showed you a domain object that had 25 parameters to its constructor, you'd be really worried, wouldn't you? What if it was a message? That's not nearly as bad, is it? And the reason I put them in the constructor is because I wanted them to be read-only. There's all sorts of things where it might be really bad in one place and it's perfectly okay in another. Keep this in mind. Do not use these metrics as a word from God. They are to be interpreted. Understanding this allows you to get a higher level perspective of your code. And having that higher level perspective is what really allows you to get and be productive in very short periods of time with new code bases you've never seen before. The reason it allows you to be productive is because it allows you to remove your fear. You have a better understanding of how things are connected, and your fear is removed about changing something and breaking something else. Now with that, I think we have about 3 minutes for questions. Does anybody have any questions?
Did you immediately start with an idea to provide such high-level information, or did you see it at some point?
Actually, this is quite funny. When we were first building out the tool, our main goal was to only run the unit tests that needed to be run based on the code that you changed. We worked on that use case for about a year. And all of the kinds of things, like the little risk metrics and the graphs, and most of those were internal debugging tools, and they ended up becoming the real value in the software. There's another little guy that'll pop up. We call him Gary. If your test becomes slow, the icon will turn into a snail. And he'll spit out a message saying you just made the test slow. All of these kinds of things came about organically, but my personal favorite is the graphs, because the graphs were actually my personal debugging tool. And they ended up becoming one of the main values of the software.
What's your plan to do next?
We will continue supporting it. We, at this point, don't have a... So one of the things we're looking at doing is when I have all of these metrics, in particular, for me, what's really interesting is the rate of change. Like, as you're typing, and I do your build, and I get the metrics from the line of code you just wrote, did you add or remove complexity? I want to focus a lot more on giving you real-time feedback about the quality of changes that you're making. Maybe with some guidance, like I saw what you just did, and I think you should put an interface in. For me, that's really going to be the future of a lot of our development tools, is kind of, not Clippy so much, maybe a little bit less patronizing than Clippy. But the general idea that you kind of have a pair programmer built into your IDE who's watching what you're doing, and he's giving you, well, he's a normal pair programmer, so he's actually giving you a lot of critical feedback. He doesn't tell you when things are good, he tells you when everything's bad. We could.
How do you deal with different languages? Let's say you have HTML, JavaScript, and then dependencies.
As of now, there's no good way of dealing with that. You would have to write something that basically an adapter for every single one of them that brought them back up into something else. JavaScript in particular is very, very difficult to do this kind of stuff with. How many of you have heard the dynamic versus static language debate? What's really interesting for me about the debate is that everyone compares, let's say, Java to Smalltalk or Ruby, and they say, look how much more productive I can be in Ruby. No one ever talks about you put all of this metadata into your code that describes how your code actually works. No one talks about all the tools that use that data. When you have a static language, I can tell you things like what you're actually coupled to at runtime. Can I do that in Ruby or JavaScript? Well, yes, on any given run, but that doesn't mean that that guarantees that that's all that does it. This also leads us into a fun problem. How many of you have tried to quantify how good your tests are? That's a hard problem, isn't it? So we've been playing with a way of doing this. What if I were to start randomly changing the IL of your code? There's a couple tools out, I think, in Yahveh. I haven't seen them in .NET yet, that they'll actually do this. They will go, you were adding 1, it'll add 5. Does a test break? It will basically go through and start manipulating your code to try to figure out if your tests are actually catching the random failures it puts into your code. And the way that you figure out if your tests are any good is if they break. It's very similar. I have been building a database lately. And one of the things I have them do is I have them use lots and lots of randomized testing. And the question I would always get from them is, so we built these randomized tests, but how do we know if they're any good? And there's a really simple answer to this. It's how many bugs did they find? If you wrote randomized tests and they don't find bugs, it means that your code is not correct inside the tests. You will almost always find at least one bug doing randomized testing, something you missed, some weird edge case. There's some great tools in Haskell in particular. Has anyone heard of Quick Check? It does randomized testing associated back to your code, and this is something I think you're going to find as a trend over the next, let's say, 3 or 5 years, is a lot more randomized testing, especially for edge cases. Any more questions?
Is the dragon for uncharted territory, or is it purely dragons?
Yes. It actually pops out in the tooltip and says, in the old days, they used to put dragons on the unknown regions of the map as warnings to sailors. This is your warning. Any other questions?
Is there a way of exporting those graphs?
As of now, yes, but it's a pain. You can export them as PNGs. So you would bring up a graph, export as PNG, bring up a graph, export as PNG. One of the areas we've looked at going into was basically the ability to do a batch run where you could print out all of the graphs, let's say, your entire source base. Any other questions? Well, I guess as the last speaker today, I will thank you all for coming out, and I will no longer keep you from getting your beer. Thank you for having me out.